All right. Welcome to Scaling Up Research Production with PyTorch and MLFlow. I'm Joe Spisak. I'm the PyTorch product lead at Facebook. I look after all things PyTorch here within the company, whether it's research, whether it's production usage by partner teams like Oculus or Instagram, but also probably my most passionate part of the role is building community around the project, of which we have a very large community. So agenda for this talk, I wanted to give everyone an overview of what PyTorch is, if you haven't heard of it. I'll give you a little bit of a primer, a view on the amazing community that we do have, which spans from the independent developer all the way through to industry labs and top trillion-dollar cap companies that are using PyTorch for both research and production. A bit about how Facebook uses PyTorch within its own products. And then I'm actually going to dive into some challenges, anywhere from developer experience all the way through to training at scale and deployment at scale. And then I'll finish up with some resources on how to get started. So if you didn't know, PyTorch is an open source project, and it resides on GitHub. And you can see the GitHub page here. This is the README, and you can see we have over 1,400 contributors now. I think this is an older snapshot at $13.99, and it's been around for about just under 3 years. Again, 100% open source. Everything is operated in the open. We do RFCs. We have community members from NVIDIA, from OpenAI, Google, Microsoft, and a whole lot of other people. And if you kind of look at PyTorch in kind of the areas we invest or kind of the tenets for the project, fundamentally it's this eager and graph mode, graph-based execution. So one of the things that's really cool about it is it feels like it's Python. So that gives you this kind of eager, imperative Pythonic front end. But we also have this bridge called Torch script, which I'll talk about a little bit later. It allows you to create a graph that can then be executed, in our case at Facebook, trillions of times a day. It's also dynamic. So if you look at the kind of the next generation or even the previous generation of neural networks, they're highly dynamic. So things like control flow, or neural networks with variable length data. This is kind of the world we live in with transformers and all these really funky architectures that are coming out of research that are pushing the state of the art. We want to get those into production. Thirdly, distributed training. This is something that has been supported for quite some time in PyTorch, but what we've seen is really a need for, especially model parallel in really scaling up, especially as of late. When you look at, for example, GPT-3, which just came out a few days ago from OpenAI, it hits 175 billion parameters. And I'll talk more about those types of models later on. Fourthly, hardware acceleration. We definitely live in this heterogeneous accelerator type world, whether it's a GPU or it's a TPU or FPGA or whatever. And then lastly, probably the most important tenet for the project is this concept of simplicity over complexity. And the goal here is to basically get out of the way of the developer or the researcher, make it easy, make it something that is really enjoyable to use and kind of just generally gets out of the way and accelerates whatever they're trying to do. So when we take a step back and we think about our overarching mission, it really is this research to production paradigm. So how do we take the most cutting edge research that's being prototyped by some of the top labs in the world, maybe it's Tesla, maybe it's Facebook, others, and be able to provide this production deployment path. So really creating that flywheel from research to production. And really when you look at PyTorch, to enable that, we create a number of APIs and libraries. So PyTorch itself is this kind of like really cool project, and people kind of see the end results of it. But when you look at actually what's inside of it, it's actually a number of APIs and libraries. So torch.nn, which is really this neural network library, which provides things like layers, or in our case, modules. There's things like Torch Optim, which gives you maybe a stochastic gradient descent or some some type of optimizer when you're training your network. Utilities, for example, like Torch Data for loading data sets. And then down at the bottom here, things like autograd. So kind of the beating heart of PyTorch is really this concept of auto differentiation, which basically gives you a very easy way to do backpropagation. And then as an example, Torch Vision, but we also have Torch Text and Torch Audio for things like models and data sets, as well as transformations. And then when we think about our production story, we have this library, set of APIs called torch.jit. And this is that bridge I talked about between that eager Pythonic mode over into this kind of graph production, large scale type mode. Okay, so I'm going to talk about the community now. So one of the things that gets me really passionate about this project is really building community, and the community that I personally get to engage with on, frankly, a daily basis. And so when you look at the community itself, it does span kind of everything from academia to these power users to community builders like, say, Jeremy Howard. And you can see like the tweets and the messages here. It's, it really is a broad spectrum of folks. So it could be, for example, some of the examples at our DevCon last year, we do annual developer conference, whether it's Dolby or whether it's Andre Karpathy from Tesla, or it's like the partnership that we launched with Google and Salesforce around cloud TPUs and supporting kind of the latest and greatest hardware there. This was a build, but you can kind of get the gist of it here. So one of the things we found is the community just absolutely loves the project, especially researchers. When you look at O'Reilly and the numbers they've gathered and the polls they've done around the community. Preferred Networks is a Japanese company, a pretty large startup, and they developed a really great library called Chainer, which is now migrating over to PyTorch. And then lastly, OpenAI. So I think everyone has heard of OpenAI. They have made PyTorch their framework of choice, and they're building all of their AI on that going forward. And so let's talk numbers. So I mentioned the contributors earlier. We are over 1,400 now. That's actually, when you put it in perspective, over 50% year-over-year growth. So from a contribution perspective, our community is growing rapidly. We also have PyTorch forums. So this is basically a discourse site that we moderate and manage. We have community members that answer questions and moderate and admin the site. And this is incredibly fast growing as well. We're now close to 30,000 forum users. This is something that is really amazing to watch. It just keeps growing. We don't really use Stack Overflow. We use this forum, and the community does come together, and they cover anything from mobile deployment to how to use Torch script in production to just general question and answer. Okay, and another set of metrics. So if anybody hasn't gone to paperswithcode.com, this is actually a great resource if you're into machine learning. And if you go to paperswithcode.com/trends, you'll actually see this graph, and it gets generated on a daily basis. And what it does is actually looks at the paper implementations grouped by framework. And you can see in the case of PyTorch, it does continue to grow. You can see it in red there. The blue is actually the blue is actually other frameworks besides PyTorch, and then the orange is that other framework by Google. But overall, the project continues to grow, and the number of implementations out there continues to grow as well. Okay, so switching gears, I want to talk about PyTorch briefly at Facebook. So we do use it for quite a few different applications, whether it's computer vision, whether it's translation, NLP, reinforcement learning. Again, this was kind of an animation, but you get the picture. In this case, we use it for search. We apply ML for translation. So for example, like FericSeq is a library we use, for sequence to sequence and translation. applications, of course, ads, feeds, and you can see face tagging. So quite a few different areas we apply ML. A lot of it does use PyTorch. And then this is also something that you should definitely check out. So if you haven't used a portal before, they're pretty incredible. And the camera that they have is actually an AI-driven camera. So it uses under the hood some computer vision, namely a variant of Maskar CNN, and actually does a really nice pan and follow and resize along with how you kind of engage with the screen. If you're moving around in the image, it will actually follow you quite nicely. It's really great for video conferencing with spending time with family. I use it all day, every day for all my meetings, so I've gotten used to it. I'm actually disappointed when a camera doesn't follow me. So I definitely recommend checking out the portal. And by the way, all of this actually runs on the device. So the neural network is actually running resident right there on the device. So it's not actually sending anything to the server. So your latency is super low and it's not sending any data anywhere. Okay, so I want to actually get to the meat of things here and talk about some of the challenges that I see in scaling AI. That's really the heart of this presentation. And so the first challenge I want to get to is really the developer experience. And so I think you can make something really powerful. You can make it really, really performant. But if your developer experience isn't such that it makes people delighted and want to use it, frankly, they won't end up using it. So when we think about PyTorch itself, we think about really three areas when it comes to DevX. And one is really giving someone the full freedom to iterate and explore the design space. So whether that's in NLP and large scale transformers, or it's maybe something like computer vision and object detection. We want to give them that ability to kind of use PyTorch to its full extent to be able to kind of express any idea they have. Second is clean and intuitive APIs. So in PyTorch, it's really in most cases one way to do something. There might be a couple different ways depending on what you're trying to do, but largely we try and make sure that it's an intuitive way to do things, and that the API is clean. It doesn't have a lot of kind of extra sugar in it. And then thirdly, there's a rich ecosystem of tools and libraries. So we try not to keep too much in the core. We try and keep it clean, but then have a really rich ecosystem of kind of things around PyTorch. So whether you want to load data from vision data sets or you want to do Bayesian optimization, there's a really nice set of tools around it so that the core library itself actually can stay nice and lean. So I do want to walk through some code here to kind of give everyone an idea of how nice the API is, and then I'll talk a little bit more about some of the other things around PyTorch. And if you notice in this case, we actually have Python on my left and C++ on my right. So first thing you should notice is that the APIs are very, very similar. This is actually by design, of course. We thought, long and hard about how a C++ API should look. And we really wanted this to be as intuitive as the Pythonic interface. Obviously, there's a few more colons in the C++ version, and you have to compile it and all that good stuff that is required with C++. But it does give you this feeling like you're still writing Python, but you get all the performance and all of the capabilities of actually operating in C++ land. So starting on the left, I'll just walk through briefly on the Python side. So first thing I'm going to do is import Torch, of course. Then I will set up this class called net, which inherits the Torch NN module API. And then I will start to define a network. In this case, it's pretty simple. It's two fully connected layers using the Torch NN.linear layers, which comes from the module API. I will then define a forward method, which gives me my nonlinears and maybe my my dropout layers and such. So I'll define a rectified linear unit here based on the that first fully connected layer. I'll apply a dropout with a probability of dropping out nodes at 50%. Then I will do a sigmoid nonlinear based on the second fully connected layer, and I'm going to return that at X. And you can see on the right, basically it looks pretty much the same. So C++ is basically very intuitive. And so moving on, we actually we have our net, which equals the net that we defined based on the previous function there. We are now going to set up our data loader. So our data loader comes from our torch.utils.data.data loader. In this case, we're coming from Torch Vision, which is a really handy library for loading computer vision data sets. We can load MNIST into the period/data folder. We are going to define our optimizer, in this case, stochastic gradient descent. And then we're going to set up our training loop. And in this case, our training loop is basically 1 to 11 epochs, which is iterations over the data. Over that data, we will leverage our data loader to then first zero out our optimizer, zero out our gradients, do a forward pass. So basically, zero out, then do a forward pass. Then we're going to do basically a backward pass later. But first we define our loss function. So in this case, we're using a negative log likelihood loss based on our kind of y and y hats, our prediction and target. We will then do a loss backwards, which basically is a back propagation through the network. And then we do an update, so an optimizer.step. And then we have an if statement at the end if we want to actually do a checkpoint. And in this case, we're using the torch.save API. And that's basically it. That actually gives you, that will give you a trained network at some checkpoint, depending on where you choose. So that obviously was a very simple example. And if you go to pytorch.org, there are incredibly complex versions, whether it's reinforcement learning or NLP. But that kind of walks you through the basic structure of a PyTorch program. Next are tools and libraries. So if you, for example, would like to do Bayesian optimization, if you have a number of hyperparameters you want to sweep over, and you want to do it in a better way, that's that's not a a grid search or a random grid search, this is a great way to do it. There's also frameworks for example, like 3D or differential rendering, AI like PyTorch 3D or private AI with Crypten or interpretability with Captum. And then if you go to pytorch.org and you click on the ecosystem, you'll see dozens more really great libraries and frameworks from the community. So pretty much whatever you need, it's definitely out there. Someone has built it, somebody's implemented it, and there's a great set of tools and a community to leverage. Okay, so switching to challenge number 2. So model size and compute needs. This is a really interesting one, especially for where we are in kind of the progression of things. So as I mentioned previously, the GPT-3 models just dropped this week from OpenAI. This actually isn't updated in this slide, but you can definitely see over time the parameter counts. At the time of creation of this slide, you can see the Turing NLG 17.5 billion parameter model from Microsoft was actually the largest. We had actually open sourced the BlenderBot a few weeks back, which is, there's a couple different versions of 9.7 billion, I believe there's an 11 billion parameter version. But the point is that parameter counts are continuing to grow and they're not slowing down. And we've obviously just taken an order of magnitude leap just in like the last couple of days. So this is a problem that we will be facing for quite some time. So how do you take these models? How do you run something that's state of the art like this and actually do inference and actually deploy it at any kind of reasonable scale? So the answer is actually, of course, model compression or model distillation or model quantization or pruning. And so PyTorch actually has quite a nice set of APIs for this. We'll start with the pruning API, which was new for, I believe, 1.4. In this case, these over-parameterized models are really, really hard to deploy. If you look at, for example, like BlenderBot, which is nearly 10 billion parameters. It's, today, our researchers have looked at, what it takes to actually do an inference, and we're actually running up into the 4 volta level compute just to do inference, which is kind of crazy. So really the goal here with pruning is to identify, areas where we can reduce the number of parameters without sacrificing accuracy. And there's a bit of an oversimplified code snippet here on the right. Of course, we have our trusty Linnet, which is an old school network from Mr. Jan LeCun. and a couple of if statements. So based on the modules that are kind of contained within the network, you can actually define what percentage of the actual model weights that you actually want to prune. And if you look at just the first if statement here, we're looking at torch and then com2d, which means I'm actually going to be pruning weights on the 2D convolution layers. In this case, 20%. And you can see in the second there, we're actually doing a prune of the linear layers. So I will do a else if and define the torch NN layer, and then in this case I'm going to prune actually 40% of it. So this is a really nice way and very easy API for someone to go off and prune away and experiment and figure out, hey, maybe I can prune a little bit more here from these layers, maybe I can prune a little bit less from those layers, and reduce the overall parameter count of the model, and get it to be much more efficient than it is as it stands today. Another technique that's very popular, especially with hardware supporting things like 8-bit integer and sometimes even lower precision computations, is quantization. And I mean, fundamentally, inference is expensive, especially when you start to get onto mobile devices and Raspberry Pis and other types of devices. There's limited resources. There's limited memory. There's limited compute. There's typically not the resources you would have in say a cloud or a data center. And so you kind of have to do with what you have. And so what we found is, quantizing models really does enable inference at scale. We've been deploying quantized models at Facebook for years and years now, and mainly on servers, but also certainly on devices as well, like phones. And you can see on the right here, this is again a highly simplified walkthrough of the API. But what I'm doing here is actually importing a ResNet 50 model, which is a pre-trained model. I'm actually loading the state dict, which basically gives you a fully loaded set of weights. I'm going to prepare, doing this using the quantization.prepare API, which basically makes essentially a copy of the model. I'm going to load then a config, a Q config here, a quantized config, which basically tells PyTorch, what layers I want quantized, at what configuration, and what libraries it's going to be using. So in this case, it could be using like QNNPack or FPGem. And then what I'm going to do is actually run this for loop, which actually gathers some statistics. And then I use the quantization.convert to then use the statistics that it gathers, as well as the QConfig, to then output a quantized model. So it's a pretty nice API. This is all done in eager mode today. And in the future, we have a graph mode version that we plan to bring into one of the upcoming releases. And when you look at the results from quantization, it's really interesting. So here's a couple of models here, starting with the ResNet 50, which we just talked about. Top one ImageNet is 76.1% accuracy. We lost 0.2%, but we actually improved over 2x on CPU inference. MobileNet V2, we saw a big gain, a little bit of a loss, 0.3% top one ImageNet, using quantization-aware training, which is a little more complex. It's actually doing quantization, kind of fake quantization while you're actually training the network in order to gather statistics, and then doing quantization once it's trained, using that information. We actually saw a 4x speed up improvement. And then lastly, FAIR-seq, this is really a translation or seek-to-seek model. In this case, we're aiming for basically no loss of BLEU score, which is how translation is measured. And in this case, we lost really nothing in BLEU score using dynamic quantization. And we saw a 4x improvement for running on Skylake. So pretty impressive overall. This is available today. Okay, so the next challenge is really how do we train models at scale? So in this case, we've already touched on training models at scale quite a bit. I do want to talk about it a little more in depth and actually jump into some of the libraries that we're actually using here. So in this case, this is a really nice progression that we've seen for example, like our ads and ranking models, starting with decision trees, going to these sparse linear regressions over to deep learning, to sparse NN. And then of course, we're actually beyond that now, and working on some other crazy stuff. But the point is, like, these ideas are getting even more complex, and the models themselves are getting larger and larger and even more complex. And so we needed to actually develop a number of tools to be able to address this. And to give you kind of an idea in context, just looking at like the computer vision space, starting out with like ResNet 50 maybe takes a couple of days to train. ResNet 101 takes maybe 4 days. Like the ResNext 101 larger model takes about maybe 7. Moving to a larger ResNext to 14 days. And actually, some of the things we're seeing with especially these large video data sets and video models is some of them actually can take months to actually train. So we're kind of running into a situation where if it's running for months and we get some issues, or we run into maybe infrastructure that maybe a node goes down, we could actually be in real trouble. The other thing to mention is, we actually have to deploy heterogeneous hardware to actually run training at this kind of scale. So we actually have to think about things in kind of HPC land, like how do we scale over, a faster interconnect, or larger CPUs, larger GPUs, or ASICs. And if you look at some of the cloud TPU stuff we've been working on with Google and Salesforce, this is exactly that. It's really taking the HPC mindset and be able to scale it on this heterogeneous hardware. The other thing to consider is, these types of jobs, like ML is not a regular type job from a classical infrastructure mindset. So these, data pipelines that can be, pretty predictable, et cetera. Those are great, but they're definitely not like ML jobs. What we see is more ad hoc jobs. So these are large, long-running jobs, basically, that frustrate the hell out of our infrastructure people and anyone trying to predict any of the demand that we have. We also see cost and efficiency challenges. So the ROI on these jobs is really hard to estimate. So how do you estimate the ROI on maybe running 1,000 GPUs for several weeks and maybe potentially not even getting results that you can actually deploy in production? And then fundamentally, when you're running at this sublinear scaling plus huge scale, so maybe I'm not getting, all of the efficiency out of the hardware itself, but I'm using a lot of it. It's a really easy way to waste resources. You waste power, you waste, person's time. There's environmental impact, et cetera. So there's a lot that can be really wasted when you're running these jobs, and a lot of them. So one of the things we did is we built something called PyTorch Elastic, which is used by a number of teams at Facebook. And what it really allows you to do is run in this kind of fault-tolerant and elastic environment. So when you're running these jobs on, say, maybe hundreds of servers, potentially even thousands of servers, and you're running some of these really large, say, transformer jobs, being able to operate when maybe a server goes down, maybe a disk gets full, maybe there's in the data center, there was one of the servers itself had a power spike or something along that line, and there's actually an issue, and that actual server goes down. Do you want that job to die or not? In this case, we actually allow for that fault tolerance, which is very similar to how things operate in a cloud. In the case of dynamic capacity management, when you're kind of leasing this capacity that can be preempted, maybe somebody took that server from me, they preempted my job, like in the case of, say, an AWS Spot instance, or maybe a Google Cloud preemptible instance. How do I keep running my training job when I was trying to leverage that Spot instance because it's much cheaper to run on those? And then, of course, how do I auto scale? How do I dynamically adjust, my job basically when maybe that node comes back up? So this is really handy stuff. And it's great for production teams, especially when they have these mission critical, you know, jobs they're trying to train. So I definitely check out PyTorch Elastic. Most recently, we integrated with Kubernetes, along with working with Amazon as well as Microsoft. And so there's a nice Kubernetes controller there that is supported by EKS at AWS as well as on vanilla EC2. And then, of course, Azure also uses it and supports it. But what if my scale is really large? So what if I'm in the tens of billions of training examples? My models are larger than the machine itself. I might want to run hundreds of experimental jobs, and they're all competing for resources. This is actually well, definitely an understatement from Facebook's perspective. But what if I'm running 1,000+ different production models? Um, this is actually another problem you might want to solve. And elasticity and fault tolerance doesn't solve that. So we built this thing called PyTorch RPC, or remote procedural call. And basically, what this does is enables applications to run functions remotely and automatically handles that autograd and everything that goes along with that autograd if needed. So, for example, I could be running, these like I could be running parts of my network, like maybe a subgraph of my network, on a remote machine. I could be running the autograd, the auto differentiation, and so on, all remotely. Um, some of the applications that we've seen, if you're doing, for example, large scale parameter server, reinforcement learning, maybe you have like these multiple observer streaming states and rewards that you're trying to train. And then, of course, if you're running, for example, distributed model parallelism, which is more of a canonical use case for something like this. So maybe I have this really large model, maybe it's on the order of 100 or plus billion parameters, and I want to be able to kind of slice and dice that model and run it over multiple machines because it just won't fit on my large machine that I have. So let's talk more about what's actually encompassed in this API. So this is released initially in PyTorch 1.4, which was earlier this year. And basically, there's four things that are made up here. And really the RPC, which is really the user code that you give arguments to, and you have a specified destination, pretty straightforward. There's this concept of a remote reference, which basically tracks and maintains all the objects owned by remote workers. There's an API for distributed autograd. So as I mentioned, like PyTorch has this concept of auto differentiation, that it basically tracks things in a graph as it executes and back propagates through that graph. And in this case, it does the same exact thing with a very similar loss.backward API, but actually over remote resources. And then fourthly, a distributed optimizer. So much like the distributed autograd has a distributed optimizer. So for example, if I'm doing, again, stochastic gradient descent, and I want to be able to actually run that over maybe distributed compute resources or remote compute resources, I can actually use a very similar API to torch.optim, which PyTorch offers today. So and it does all of that automatic handling of the remote references, of the subnets, and makes it feel like you're just writing PyTorch, but maybe you're actually running it on remote resources. Okay, last challenge I want to go through is deployment at scale. So I think we talked about the user experience. We talked about how to optimize models. We talked about training at scale, these large models, how do we deal with that? Let's talk about once we're actually ready to deploy, what types of challenges we're dealing with. I think this is something that's a bit of a forgotten. People tend to forget about this. They want to train large models, they want to author a lot of models, but once you actually want to get into production, there's a lot of things to be considered. So first thing is really loading and managing multiple models on multiple servers or endpoints. So in this case, like it's not just one model. I might have 5 different versions of that model. I might have 20 models with five versions of those models. And I want to be able to just manage those depending on what use case or the environment, or maybe there are geographic concerns because different models are more geo applicable for different areas. especially when you talk about languages. And I'm also going to be running on multiple servers. So how do I handle all of those? And by the way, some of these might actually run on device, on an iOS or Android device. How do I handle the pre and post processing code? So I think we all tend to fixate on the model itself and those train weights, but there are, when actually doing predictions, you actually do some level of pre and post processing to handle those requests. How do I log? How do I monitor? How do I secure these predictions so that someone can't actually hack my API and make it do things that I don't want it to do? And then, of course, what happens when you hit scale, which is a problem, I would say, for a certain number of companies today. But I think the expectation is that this will be a universal problem very quickly. So one of the things we did, this is in partnership with Amazon, especially AWS. We launched this as part of the 1.5 release. So Torch Serve, it's an experimental. You can see kind of a block diagram on the upper right here, taking from multiple models through to a RESTful endpoint, to be able to serve these multiple models and be able to manage them through a couple of different APIs, specifically the inference API as well as the management API, and then be able to handle all the logging and metrics that go along with it. It has a number of default handlers for things like image segmentation, text classification, but then you can also very easily create a custom handler if you have a specific use case. There's model versioning, which is great even for prototyping. If you're trying to just do, like, for example, A/B testing, you can create a quick model version of what you're doing. If you train another model and you just want to version that as well, and be able to do a quick comparison. There is automatic batching, across HTTP requests. There's also logging with common metrics as well as custom metrics that you can actually go and define yourself. And then, of course, there are APIs for managing, both the management of your models in production as well as the inference itself. And this is, again, a very new project, partnership between Facebook and Amazon, but we were hoping to grow a community around this and really take this project to something that can scale, for a large number of use cases and be used in the enterprise space. And then, of course, I mentioned MLFlow in the title, but I haven't mentioned MLFlow yet. This is a really great community that has done some really amazing things around model management and really lifecycle management. And there is a support built in today with MLFlow.PyTorch, for things like logging and loading PyTorch models. It does use Torch Save, which basically pickles your model and serializes it through Pickle. We are looking at adding Torch script support. That's something we plan to work on. If you want to contribute to that, let us know. We also are looking at integrating with Torch Serve, which was what I mentioned previously. So you basically take this lifecycle management, log, load models into the MLFlow format, and then be able to basically seamlessly serve those in Torch Serve. That's coming soon. Again, if you're interested in collaborating on that, feel free to reach out. We'd love to work with folks. We love contributors. So please do reach out. Okay, those are the 4 challenges. Now I'm going to give everyone an update on the latest on PyTorch as well as how to get started. Okay, so if you haven't seen, PyTorch 1.5 was released in late April. It had over 2,200 commits. So it was a pretty big release for us. A couple of the key features that came along with it, I mentioned Torch Serve. This was a partnership with AWS. That's an experimental. We also released the Torch Elastic Kubernetes operator that is supported by AWS as well as Azure, which is really cool. So Elastic Kubernetes training jobs in the cloud on PyTorch. Also, the stable support for Torch RPC for things like distributed model parallel training. We added experimental support for the new high-level autograd API. So, for example, if you're doing Jacobians or Hessians or Jacobian vector products or vector Jacobian products or Hessian vector products and so on and so forth, these are really great if you're doing research. Some of the work out of Anima and Nankumar's lab at Caltech is an example. So I would definitely check those out. We also brought the C++ front-end API, which I talked about earlier on in this talk, to parity with Python, and that's now in stable point. We also added support for custom C++ classes in TorchScript as well as Python. That's an experimental. And lastly, we've deprecated Python 2. That was the last release previously that we supported Python 2. So we are 100% Python 3 from this point forward. I know that'll make a lot of people happy. We also released a number of domain libraries, so check these out. So I won't go through the details here, but Torch Vision, Torch Text, and Torch Audio all have releases. If you go to pytorch.org, you can get started. So we have really nice interfaces for getting started locally as well as on the cloud. So you can click here, you can do a little selector. It selects what maybe version of CUDA you want or what platform you're using. As well as if you click on cloud partners, there's some nice links into the various cloud providers, including AWS, Azure, Google, as well as Ali Cloud. If you're looking to get educated, we have a ton of resources. So Udacity has been a longtime partner of PyTorch. They pretty much built everything, all of their classes and 9 degrees, at least a large percentage of them on PyTorch, which is great. But we did build a free course a while back, and there were other free courses available, like the private AI one. But if you do want to get started with PyTorch and you're a beginner, this is a fantastic class. It's completely free. It takes you around 2 months. And if you basically know Python, you can learn PyTorch. So definitely check that out. There's also a number of books, and actually more books coming if you're familiar with Jeremy Howard's book. But in this case, we're showing the NLP book by Dilip Rao, a really great book, as well as the Deep Learning with PyTorch book by Eli Stevens and Luca Antiga. Another great book that we had a nice chance to review and support. So if you're looking for books, those are on Amazon. Those are available. I think there's digital copies on PDF as well through both O'Reilly as well as Meep. And I mentioned Jeremy Howard already, but Fast.ai provides a really great set of free courses as well with these kind of MOOCs that Jeremy does, as well as the Fast.ai libraries. And he has a V2 out there. And of course, his book is coming. So definitely check that out. He has an amazing community. And then if you're looking for Chinese, we also have partners, community members in China. If you go to pytorch.apachecn.org, you can see tutorials and docs converted over to Chinese. So really great. We have a really great community in China. And then I'll leave you with this last slide. So we have a number of channels. We have pytorch.org, which is our main site for docs, tutorials. There is a blog there, although we use it mainly for releases. But we definitely have some deeper tech posts that some of the community members have done. We have a Twitter channel that is very active. Our YouTube channel is also very active. We have Facebook, and then we have relatively new from last year. We started a Medium channel as well, which is 2 to 3 posts a week at least that we're seeing. So incredibly active. So I would definitely check those out and become part of the community. Let us know. Tag us on Twitter if you have a question. We'd be glad to answer that or engage in any way if there's interest. Thank you so much.